Hi everyone. Today lecture about the structures that is statically indeterminate to more than 1 degree. In previous lecture, we solved example about indeterminate structure to the first degree. Now, how we can solve statically indeterminate structure if it's more than 1 degree? We'll use the relationship between flexibility and displacement. So the relationship between flexibility and displacement can be developed to a general formula for a beam that is acted upon by more than one concentrated load, in which delta 1 is displacement due to load 1, P1, delta 2 is displacement due to load 2 or P2, and delta n is the displacement due to Pn. By using the principle of superposition, each displacement can be expressed as the sum of the displacements due to all acting loads P1, P2, and Pn. For example, the displacement delta 1 is given by the expression delta 1 equals delta 1 plus delta 1 plus delta 1n, in which delta 1 is the displacement corresponding to P1 and caused by P1. So delta 1 is the load at the position of P1 and it is due to load P1. Delta 1 is the displacement corresponding to P1 and caused by P2. The position of delta 1 still in the position of P1, but this deformation is due to P2. Delta 1n is the displacement corresponding to P1 and caused by Pn. In similar manner, n additional equations can be written for delta 1 to delta n. Each displacement is directly proportional to one of the loads. The equations for displacement can be written in the terms of the loads as follows. Delta 1 equals F11 plus P1 plus F12 times P2 plus F1n times Pn. This F11, F12, and F1n are the coefficient of flexibility. P1 is load 1, P2 is load 2, and Pn is load n. So the multiplication between flexibility coefficient and P1, the summation of them, equals delta 1 at position of P1. And the same thing for P2. And for Pn, delta n. The expression F11 times P1 represents the displacement delta 1. The expression F12 times P2 represents the displacement delta 12, and so forth. Each term of the right hand side is the displacement that is written in the form of the coefficient times the action that produce displacement. What is coefficient? F11, F12, F1n. The coefficients are called flexibility coefficients. Each flexibility coefficient F represents a displacement caused by a unit value of a load. The calculation of flexibility may be a simple or difficult task depending upon the particular structure being investigated. Instead of expressing displacement in terms of the actions, as was done, it is also possible to write action equations expressing the actions in terms of displacement. Such equations can be obtained, for instance, by solving simultaneously the displacement equation. The results action equation have the form P1 equals K11 times delta 1 plus K12 times delta 2 plus K1n times delta n. force, stiffness, deformation. Summation of stiffness times deformation equals P1 at load 1. The same thing for P2 and Pn, in which K is a stiffness coefficient. Stiffness represents an action due to a unit displacement. Thus, the stiffness coefficient K11 represents the action corresponding to P1 when a unit displacement of type delta 1 is introduced, while the other displacement, namely delta 2 to delta n, are kept equal to 0. Similarly, the stiffness coefficients K12 is the action corresponding to P1 caused by a unit displacement of type delta 2, while delta 1 and other delta are equal to 0. In matrix form, displacement equations we can convert these equations into matrix form. This delta equals flexibility matrix times applied load. Delta equals flexibility times applied load, in which delta is displacement matrix of order n times 1. F is square flexibility matrix of order n times n, and P is an action or load matrix of order n times 1. The flexibility coefficients Fij that appear on the principle of F are called direct flexibility coefficients and represent displacements caused by unit values of the corresponding actions. The remaining flexibility coefficients are called gross flexibility coefficients. The action equations for the structure which n actions P acting upon it can be obtained by solving simultaneously the above equations. This operation gives the following action equations in matrix form. So this new relation is for stiffness method that we will discuss in next lecture. P equals stiffness times delta. The relationship between the flexibility and stiffness can be represented by the given expression. P equals K times delta, or F inverse times delta. F inverse, the inverse of matrix F, equals stiffness, in which F inverse denotes the inverse of the flexibility matrix F. This method can be applied to any indeterminate structure. The degree of indeterminacy of the structure equal the number of redundant, in which the redundant is the number of forces that are more than the minimum necessary for the static equilibrium of the structure. That means the number of extra reactions, if it's removed, the structure is still stable. After that, the structure will be unstable. The outline of the method is as follows. So these steps, how to solve indeterminate structure by using flexibility method if it's more than 1 degree. First, reduce the structure to a condition of determinacy and stability by removing the redundants. That means remove the extra reactions and convert from indeterminate structure to determinate structure. The resulting structure is called the primary structure. Second step, determine the resulting error. Delta due to applied load minus delta due to concentrated load equals 0. In geometry occurred incurred by subjecting the primary structure to loads on the original indeterminate structure. Step number 3, apply the redundant to the primary structure and determine their effects on the displacement where the geometry has to be corrected. Determine the redundant to eliminate the original errors in the geometry. Last step, obtain the final forces by adding the redundant forces to the corresponding forces of the primary structures. Example 2, let's apply these steps in example 2 and how we can find the reactions for indeterminate structure to more than 1 degree. We'll explain example 2 in next video. Thank you.